Hello friends, welcome back to my YouTube channel. In this class I am going to solve 3 more problems of chapter 7 of PkNAG's engineering thermodynamics, which are based upon the concept of entropy and entropy generation. Before starting, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it to your friends. Let's get started. The question number 7.7 is like this. Water is heated at a constant pressure of 0.7 megapascal. The boiling point is 164.97 degrees Celsius. The initial temperature of water is 0 degrees Celsius. The latent heat of evaporation is 2066.3 kilojoule per kg. Find the increase of entropy of water if the final state is steam. So here the initially temperature of water is 0 degrees Celsius, and you know at this pressure the saturation temperature is 164.97 degrees Celsius. So once the temperature reaches this point, water starts to vaporize. So and for transition from water to water vapor to take place, this much amount of heat has to be provided, and that heat is 2066.3 kilojoule per kg. And we have to calculate the increase of entropy of water, and the final state is saturated steam. So if you draw the TS diagram, this will be like this. This is in fact the starting point at which the temperature of water is 0 degrees Celsius. The water initial temperature of water is 0 degrees Celsius. In terms of Kelvin, this will be 273 Kelvin. Initially, that is state 1. Water is at state 1, and this is the constant pressure heating process on TS diagram, and this is state 2. Here this is the saturation temperature or boiling point. This is saturation temperature or boiling point, and this is state 2, and this is state 3. Here water gets converted into saturated steam, and if you want to draw the constant pressure process on TS diagram, that will continue like this. Here that will be at a state of superheated steam, but our aim is to find out the S3 minus S1. This is initial state and this is the final state, and this saturation temperature is nothing but 164.97 plus 273, that is 437.97 Kelvin. So when water moves from state 1 to state 3, what is the change in entropy? S3 minus S1. So you know entropy is an additive property. So S3 minus S1 can be written as the summation of, or we want to find out the delta S. Delta S is nothing but S3 minus S1. This is the final state, saturated steam. Final state is steam. And since entropy is an additive property, we can write like this: S3 minus S2 plus S2 minus S1. So first we are to calculate S2 minus S1. Change in entropy of water when water is heated from 0 degrees Celsius or 273 Kelvin to 164.97 degrees Celsius, that is the saturation temperature corresponding to 0.7 megapascal. This line represents the constant pressure heating line for 0.7 megapascal. So S2 minus S1 is nothing but integral of d cut q by t, T1 to T2. This is equal to, since temperature is changing, so that's why dq, you know, that is mcp dt divided by t, and this is equal to mcp can be taken outside the integration sign because these are constants, T1 T2, and this is mcp. M is mass, Cp is specific heat at constant pressure, ln T with integration limits from T1 to T2, and this is equal to ln T2 divided by T1, ln T2 divided by T1. Similarly, if you want to calculate S3 minus S2, that is equal to M, you know, whenever water here at point 2 water starts getting vaporized, and here the vaporization process of vaporization ends. So during this process, whatever heat is required, that is latent heat of vaporization, but temperature remains constant at this 437.97 Kelvin. So since the temperature during this process is not changing, so the formula change in entropy will be mass of water multiplied by latent heat of vaporization, HFG, divided by T saturation. This is equal to MHFG divided T saturation here is nothing but T2, which is also equal to T3, and this is equal to, and if you, and this is equal to M into HFG is 2066.3 divided by 437.97. This is the change in entropy, and since it is given that the mass of water is, in fact mass of water is not given, so we can calculate for 1 kg mass of water, 1 kg mass of water, or specific change in specific entropy. In fact, mass is not given, so mass can be taken to be 1 kg. So S2 minus S1 will be, S2 minus S1 will be 1 into Cp. Cp is 4 for water, Cp is equal to Cb, and that is equal to 4.187 ln, in place of T2 I will write T2 is 437.97 divided by T1 is 273, that is equal to 4.187 ln 1.604. This is kilojoule per kg Kelvin. This is the unit of specific entropy. Then for S3 minus, this is in fact small s3 minus S2 is equal to, in place of mass M I will write 1 into HFG is equal to 2066.3 divided by saturation temperature is nothing but 437.97. This is equal to 4.7179 kilojoule per kg Kelvin. So the change in entropy during the total process is equal to S3 minus S2 plus S2 minus S1 is equal to 4.7179 plus S2 minus S1 is already, that we have already calculated. S2 minus S1 is In fact, this is 1.9783 kilojoule per kg Kelvin. This is 1.9783. 1.9783 kilojoule per kg Kelvin, and this comes out to be 6.6962 kilojoule per kg Kelvin. So this is question number 7.7. Now question number 7.8. 1 kg of air initially at 0.7 megapascal 20 degrees Celsius, 0.7 megapascal 20 degrees Celsius, that are the pressure and temperature at state 1, that is given to be 0.7 megapascal 20 degrees Celsius, changes to 0.35 megapascal and temperature is 60 degrees Celsius by 3 reversible non-flow processes as shown in figure. This is state 1 and this is state 2. So this condition is 0.35 megapascal 60 degrees Celsius and state 1 is 0.7 megapascal 20 degrees Celsius through 3 processes. First process is process 1A2. 1 is the initial state, 2 is the final state, and the process is 1A. There are 2 processes through which the system travels from state 1 to state 2 through 1A2. That is 1A is a constant pressure process and A2 is constant volume heat rejection, because it is an ideal gas, and so this is a constant volume process. Both pressure and temperature decreases when it travels from this state to this state. So you see, this is one process, and another process through which the system can travel is 1B2, process 1B2. 1B2, a 1B is one process, that is isothermal process. This process is isothermal, that is temperature remains constant during the process of 1 to B, and then another process that is a horizontal line is there, in fact B2. B2 is a horizontal line which is a constant pressure process, because this is PV diagram, P and specific volume. So 1B is a reversible isothermal process and B2 is constant pressure process. That's how the system is traveled from state 1 to state 2 through this process 1B2. 1B is isothermal and B2 is constant volume heat addition process. Then another process is there, 1C2. 1C is a reversible adiabatic process and C2 is another process. So and process 1C2 is an adiabatic expansion followed by a constant volume heating. C से 2 जब एयर जा रहा है तो ये हीटिंग हो रहा है, constant volume heating. This is constant volume cooling and this is constant volume heating. So we have to calculate, determine the change of internal energy, enthalpy, change of internal energy, enthalpy and entropy for each process, and find the work transfer and heat transfer for each process. Work transfer, heat transfer for each process. Take Cp is equal to this much, Cb 1.005 and Cb is equal to 0.718. Assume specific heats to be constant. Also assume for air Pb is equal to P small v is equal to 0.27 T, where P is the pressure and V is the pressure in kilopascal, small v is the specific volume in meter cube per kg, and T is the temperature in Kelvin. So you know, for all the processes, the change in internal energy, enthalpy and entropy will remain constant, because all those are properties. So point functions. They don't vary from path to path, but we can check that these are actually equal. These are actually equal values on different paths. That we can check it out. So first, for process 1A2 we will calculate. In fact, mass is 1 kg. So mass is 1 kg. Mass is 1 kg. This mass is 1 kg and pressure is 0.7 megapascal initial pressure, and T1 is 20 degrees Celsius. You see here 0.7 megapascal is the pressure, 20 degrees Celsius is the temperature. So 273 plus 20, 293 Kelvin. P2 in fact is 0.35 megapascal. T2 is here 333 Kelvin, 60 degrees Celsius. CPCB are given. So now we will calculate for process. Suppose there are three processes. For process 1A2, you see, for any process we can apply this equation Q12 is equal to U2 minus U1 plus W12. That we can apply this equation, where Q12 is the heat added to the system during this whole process. Here initial state is 1 and final state is 2. So Q12 during this whole process, Q12 is equal to change in internal energy, that is the internal energy at final state minus internal energy at initial state. Here final state is 2 and initial state is 1. But this 1A2 consists of two paths. One is 1A and another is 1A, that is constant pressure process, and A2 is constant volume constant volume cooling process. So if I can write in place of Q12 Q1A plus QA2 is equal to U2 minus U1 plus W1A plus W12. In fact, Q is for heat added to system and W is for work done by system. You see here WA2. Here WA2 is 0. WA2 is 0 because this is A2 is a constant volume process. So PdV work will be 0 for this A2 process A2. So then I can write this is suppose your equation 1. So you see small v1 or specific volume of air at state 1 we can calculate, that is RT1 by P1. This is equal to 0.287. This is given in the question. PV is equal to 0.287 T. So from that R 0.287 is the value of R multiplied by T1 here is 293 divided by, and pressure has to be expressed in terms of kilopascal. So but pressure is given in the question in terms of megapascal, so we have to convert that into kilopascal. 0.7 megapascal is 0.7 into 10 to the power 3 kilopascal. So that is equal to 0.12013 meter cube per kg. This is small v1. Then VA we can calculate. VA equal to VA is equal to V2. You see this is VA is equal to V2. VA equal to V2 because this is a constant volume process A2. So that is equal to RT2 divided by P2. This is 0.287 multiplied by 333 divided by 0.35 into 10 to the power 3 is equal to 0.27306 meter cube per kg. For process 1A, for 1A process, we know that P1 V1 by T1, this is ideal gas equation and air can be assumed to behave like an ideal gas. So PA VA by TA for process 1A. For process 1A, P1 V1 by T1 equal to PA VA by TA. Since it is a constant pressure process, P1 equal to PA. From this, TA can be calculated, and that is T1 VA divided by V1. T1 is 293, VA is 0.27306 divided by V1 is 0.12013, that is equal to 666 Kelvin TA. But we are to find out Q1A. Q1A is equal to, for constant pressure process, Q is equal to mCp delta T. Q for constant pressure process, you know, Q is equal to, this can be proved that for constant pressure process, QP for constant pressure process is equal to delta H for constant pressure process, and that is equal to mCp delta T for constant pressure process only. So Q1A is equal to mCp TA minus T1. Since m is 1 kg, so 1 into 1.005 multiplied by 666 minus 293, that is 374.865 kilojoule. 374.865 kilojoule. QA2, this is a constant volume process, and for constant volume process, heat is equal to, heat interaction is equal to mCv delta T. mCv T2 minus TA is equal to 1 into 0.718 into 333 minus 666, this is equal to minus 239.094 kilojoule. Since this is a constant volume cooling process, so it is heat, in fact in equation Q stands for heat addition to system, and because since it is a cooling process, so it comes out in terms of negative. So W1A is equal to P1 VA minus V1, and this is total volume and this is also total volume. MP1, this is specific volume, VA minus B1, and this is equal to MR, because PB is equal to RT, so MR TA minus T1. I have already calculated TA, so 1 into 0.287 666 minus 293, so this is coming out to be 107.051 kilojoule. So U2 minus U1 from the equation 1, in fact U2 minus U1 can be calculated, because I have calculated everything Q1A, QA2 and W1A, and this is already 0. By putting all these values, I can find out U2 minus U1. So U2 minus U1 equal to 374.865 minus 239.094 plus minus 107.051, 28.72 kilojoule. This is U2 minus U1, and this change in internal energy will also remain same for all these processes, because the initial and these are point functions, and these value will not depend upon path, but we have to check it out, so and we are to calculate now delta H also. In the question it is given that we have to calculate delta H, change in enthalpy. Delta H is equal to S2 minus H1, and this is equal to U2 minus U1 plus P2 V2 minus P1 V1, and this is equal to U2 minus U1 plus RT2 minus T1, and this is equal to 28.72 plus, in fact this is 0.287 into 333 minus 293, this is equal to 40.2 kilojoule. This is change in enthalpy, and we have to calculate the change in entropy also. From equation TdS is equal to du plus pdv, or I can write also dH minus vdp. So from this ds is equal to dH by t minus v by t dp. From this cp dt, dH is equal to cp dt, since cp is cp dt by t minus b by t is, you see, pv is equal to RT. From this, for ideal gas, and since it is given that air is the working fluid here, so V by T is nothing but R by P. So in place of V by T, I can write R by P dP. So if you integrate this ds, integral of ds, since Cp is a constant, dt upon t minus R dP by P. And so S2 minus S1 is equal to Cp ln and this is, so Cp ln T2 by T1 minus R ln P2 by P1, and this is coming out to be 1.005 ln 333 divided by 293 minus 0.287 ln 0.35 divided by 0.7, and this is equal to 0.3275 kilojoule per kg Kelvin. So total change is equal to m into S2 minus S1, and this is equal to 1 into 0.3275 kilojoule per Kelvin. And if we calculate all these values for all those other two processes, then these values will not change, because these are point functions and are independent of path. So next question is question number 7.9. Question number 7.9. The question is like this: 10 grams of water at 20 degrees Celsius is converted into ice at minus 10 degrees Celsius. This is initial state. Water is at liquid state, and final state is it is at solid state. So definitely there will be decrease in entropy. So because the entropy of a substance is high state gaseous state, and then it some decrease takes place when it is converted into liquid, and in fact entropy is at its lowest when a substance is in solid state. So here definitely entropy is decreasing at constant atmospheric pressure, assuming the specific heat of liquid water to remain constant at 4.2 joule per gram Kelvin, and that of ice to be half of this value. Specific heat of water is 4.2 joule per gram Kelvin, and ice and that of ice to be half of this value, that is 2.1 joule per gram Kelvin, and taking the latent heat of fusion of ice at 0 degree Celsius to be 335 joule per gram, and taking the latent heat of fusion of ice at 0 degree Celsius to be 335 joule per gram. Calculate the total entropy change of the system. Initially the water is at 20 degree Celsius, and then finally it is converted into ice at minus 10 degree Celsius. Since the atmospheric pressure is the pressure here, so saturation temperature is 0 degree Celsius. So there will be, the process will be like this on TS diagram. On TS diagram, if you draw, the process will be like this. This is suppose state 1, and here the temperature of water is 20 degree Celsius, and in terms of Kelvin it is 293 Kelvin. And here suppose state 2, here this is converted. In fact, the temperature of water decreases from 20 degree Celsius to 0 degree Celsius, that is the saturation temperature at this atmospheric pressure, where the phase change takes place. And this is suppose the saturation temperature is 273 Kelvin. Then again the temperature decreases from 0 degree Celsius to minus 10 degree Celsius. Here it is from by moving from state 2 to state 3, water is converted into ice, and then again the temperature decreases. So line will be like this. This is suppose state 4, and this is minus 10 degree Celsius, that is 263 Kelvin. So here the line is horizontal because no change in temperature takes place here, only decrease of entropy takes place. This is your specific entropy. So in fact, while moving from state 1 to state 2, entropy decreases. Here also in all these three components the decrease in entropy takes place, but during this process of 2 to 3 only decrease in entropy takes place, no change in temperature is found. But during the processes 1, 2, when the water is cooled from 20 degree Celsius to 0 degree Celsius, both temperature and entropy decrease. And when ice is cooled from 0 degree Celsius to minus 10 degree Celsius, then also both entropy and temperature decrease. But during the process 2 to 3, only decrease in entropy is there, but temperature remains constant at 0 degree Celsius or 273 Kelvin. But we want to find out S4 minus S1. S4 minus S1. So S4, this is the final state, this is the initial. S4 minus S1, since entropy is an additive property, so I can write S2 minus S1 plus S3 minus S2 plus S4 minus S3. This is S4 minus S1. So now S2 minus S1 is equal to ds is equal to integral of dq by t. Integral of dq by t is equal to mcp dt divided by t. d cut q is mcp dt. So here the initial temperature is 293 and final temperature is 273, because initial state is here 293 Kelvin and here the temperature is 273 Kelvin, 0 degree Celsius. So this is equal to mcp can be taken outside because those two are constant. dt upon t, 293, this is 273. This is equal to, in place of mcp I can write m is 10 gram. If you convert that into kg, 10 gram will be 0.01 kg. multiplied by Cp is 4.2 joule per gram Kelvin. In fact, it is most of the times it is expressed in terms of kilojoule per kg Kelvin, and this is also 4.2. This is in joule per gram, and this will be same as kilojoule per kg, because if you multiply the numerator by 10 to the power 3 and denominator by 10 to the power 3, there is no problem in. So this will be equal to this. 4.2 joule per gram Kelvin is equal to 4.2 kilojoule per kg Kelvin. So this is 4.2 kilojoule per kg Kelvin, and this is ln 273 by 293, and if you calculate this, this will be minus 2.9694 joule per, in terms of joule, this will be equal to minus 2.9694, and in terms of kilojoule per Kelvin, that will be minus 0.0029694. So then for S3 minus S2, S3 minus S2, this one, S3 minus S2, that will be minus, here only heat rejection takes place, because this is water is converted into ice here. So that means latent heat of condensation has to be extracted. So latent heat of fusion has to be removed. In fact, this is a process of freezing. So minus m, this is L is latent heat of fusion, divided by saturation temperature T, 10 gram. If you convert that into kg, and latent heat is given to be 335. You see, this is 335 joule per gram, 335 joule per gram. So it will be kilojoule per 335 joule per gram, means this will be ठीक है, ये जूल में रखेंगे 335 जूल पर ग्राम, बट 0.01 kg, और आई कैन राइट दिस डायरेक्टली 10 minus 10 into 335 डिवाइडेड बाय 273. ये है m है 10 ग्राम और लैटेंट हीट है 335 जूल पर ग्राम. सो इसको डिवाइड करने से -12.271 जूल पर केल्विन. नेक्स्ट इज S4 minus S3. S4 minus S3, this one, S4 minus S3. When ice is the temperature of ice decreases from 0 degrees Celsius to minus 10 degrees Celsius. So this is equal to, initial temperature is 0 degrees Celsius and final temperature is 263. D cut Q by T. This is mCp dt by T. 273, 263. This is equal to, mass is 10 gram, and if you convert that into kg, 0.01 into Cp is half of that of the water, that is half of 4.2. 4.2 divided by 2 dt upon T. 273 and limit is 263. This is equal to 0.01 multiplied by 2.1 ln T2 by T1. This is equal to 0.01 multiplied by 2.1 ln 263 by 273. 263 by 273. This is minus 0.3882 joule per Kelvin. This is 0.01 kg, and this specific heat is in terms of 4.2 joule. So in fact this will be 10 multiplied by this will come out to be this much. So next we have to find out S4 minus S1. S4 minus S1 is equal to S4 minus S3. All these values are to be added. Is equal to minus 15.6286 joule per Kelvin. So total entropy change is this much, or you can say total entropy decrease is 15.6286 joule per Kelvin. So thanks for watching.